For those of you that just joined, the files are located here, the code as well as instructions to get to the data, so on and so forth. All of that can be located on the bit.ly link that you see here. The class videos, the one that I just started, the recording, will be posted by the Sunday after class on my website. My website is www.kelseymnet.com. You're also welcome to go to this YouTube channel here. I generally post that, and if you subscribe, you'll be able to know when a new video is posted. I do a PySpark class as well, so everything that I do will be located at this YouTube link. So please feel free to go there as well. So I'm going to leave this up for a couple more seconds, this bit.ly link, and then I'm going to get started. All right, just going to come back and check my code. Yep, still running. All right, going to go into presentation mode. I am not able to use two screens today, so I cannot see the chat screen. So please, if you do have a question, feel free to unmute because I won't be able to check that chat today. And normally I would have the two screens, but that's not the case. Hold on, gotta let that person in, admit. All right, so getting back to our PowerPoint, first off, if you're joining for the first time today, my name is Kelsey Emnet. I actually just started a new position at Merits as the director of the Decision Sciences department. So my background is in machine learning, big data analytics, and I work a lot on the cloud and helping with cloud migrations. And I work primarily in Python and PySpark, but I've worked in R pretty heavily as well. I'm trying to get into admit that person. Okay, I think we're good. All right, thanks whoever did that. So I will be showing this code in the demonstration in Python itself. So So if you're on two axes, like we're seeing in this particular instance, you'll have an X and a Y coordinate. So you would use when you're taking two different coordinate, you have one value will have two coordinates, an X and Y coordinate, and the one that you're measuring the distance to will also have an X and Y coordinate. So it's pretty self-explanatory. You take the coordinate of one for the X coordinate and subtract the X coordinate of the other. You square that, and then you take the Y coordinate for your first one, subtract the Y coordinate for the second one, and then you square that. And then you actually, whatever you get for this sum, you find the square root of that there. So that is what Euclidean distance is. In general, that's the one I tend to use. One thing that I notice with almost every machine learning model is that the difference between what I just showed you, Euclidean distance, and Manhattan distance, which is the other main one that you may use. The accuracy difference is usually minuscule. There's almost no accuracy difference at all in almost every case I've seen. The Manhattan difference, if you're going to see a difference, it would be if you have many features in your data set. Manhattan difference actually, it handles that a little bit better. But that's here, it looks very similar, but you're taking the absolute value of the first X coordinate minus the second X coordinate plus the first Y coordinate minus the second Y coordinate. You can think of the Euclidean distance as finding the shortest path between 2 points. Manhattan distance is actually, you can think of it more like city blocks. So you would have, say, a house here, and you had to travel down and over in order to get over. So it would be looking at like finding a perpendicular line to go to both of them. So city blocks versus the shortest distance between 2 points. So I'm going to come down and show you how you would be able to actually test the different machine learning models. A lot of these are going to be for future classes that we look at. But in general, when we have different hyperparameters that we are tuning, and we use something called a grid search. In this case, I'm grid searching or trying 4 different values of K. So in one case is 5, 8, 12, or 15. So I'm going to test out all 4 of those values. And then I will dynamically put them into my different models. So in this case, in scikit-learn, which is the Python, say, not scaled version. It's the easiest way to learn machine learning. You just actually place those values dynamically into the K value here. The P equals 2 tells us which distance metric we are going to use in each case. And then actually the number of jobs is something that's for efficiency's sake. So if I have 7 cores on my computer, it's going to do the distance comparison on multiple cores at the same time, so it finishes earlier. So that is how you would do a grid search. And in this case, I actually did the Euclidean distance first. And you'll see down here so this one would actually be, the Euclidean, and this one would be the Manhattan difference. All right. I'm going to toggle back here. Are there any other questions before I move on to overfitting and underfitting? Okay. All right, so one of the big things that you're trying to manage when you're doing hyperparameter tuning is overfitting and underfitting. So the overfitting is when a model is overtrained or too closely matched to your training data set. So you can think of it as, instead of actually learning the patterns, the model is just memorizing your training data, so that when you actually take that tomato, that new value, and then you put it into your model and try to predict whether it's a fruit, protein, or vegetable, it's going to pick that more because of it memorized the training data than what the actual relationships are. So in general, often overfitting occurs when you have too many features in your machine learning model, which is when you would use feature selection and take those most important features and make it so that your model has fewer features. Or you don't have a big enough data set to be using machine learning, because in general, at the very minimum, you would need several thousand data points in order to do a machine learning model. So that, and then the other reason you might be overfitting is if you're using a model that is too complex for the amount of data that you have. So if you try to run a neural network on 1,000 observations, you're going to overfit your data. It's 100% sure. Neural networks generally require tens of thousands of data points versus a small number. So linear and logistic regression are going to do a lot better with smaller data sets because they're a lot less complex. So that is what overfitting is. Underfitting is when a model is not complex enough to accurately capture the relationships in the data. So for instance, the data that we're using in this case for this particular exercise is very messy. So individuals in substance abuse treatment centers are coming in and they are writing down these patient characteristics. And with those patient characteristics, they're probably not focusing very much on data entry. They're focusing on their patients. So that's something to keep in mind. And there's a lot of missing data. So the model has to be pretty complex, and you have to use a pretty large sample size in order to make a model that correctly will fit those relationships and be able to understand and predict those relationships. So we've already talked about what these are impacted by. So the goal with hyperparameter tuning is to find the right balance between overfitting and underfitting. Down here is a great example of what overfitting looks like and what underfitting looks like, and what the happy medium might be. So the overfitting is, you can see that it has really, in reality, memorized the training data. So there's a very close squiggly line here that takes the plus signs and the zeros. So it's probably overfitting if it looks something like this. Right here, the line isn't actually capturing the real relationships. The data points are more complex than this line can actually show. And then in the middle here, there's a good compromise. So where your X's and O's, it's getting one wrong, but it's putting a pretty a simple line or curve in between it. So it's a good compromise between the two. All right. Is there any other questions? Let's come back and making sure this goes right. Yep, that's not good. Okay. So I'm not sure what's going on there. I apologize. I might be able to not actually show some of the things that I wanted to show. It's one of those points where your code works the first time, but it's not working the second time. All right. So model evaluation will be what we'll cover in just a second. So coming back real quickly, we would normally take a grid search and go through, and in the case of scikit-learn, we're using the k nearest neighbors, setting our nearest neighbors. We then use something called a fit. This it goes through and it takes the data set, in this case, the X train small, and it takes that, it runs and fits the model to your training data. In the fit method, it takes our known data points, so our training data, where we actually know the features and the predicted value. It trains a model with it that tries to predict that ground truth. So with the features we know and the actual predicted value that we know. So it trains that model, and then with the predict method, it takes that validation data set. So something where we're actually trying to predict the accuracy of another group of data that was randomly chosen from our original data frames. So that validation data set, we are not actually using the predictions to do anything, but we're using that to then place into our model. And then we make a prediction. And then we can actually output based on what we know the real answers are. Things such as accuracy. We can output recall, precision, and other things that are able to go to evaluate the accuracy or the value of your model and how it is predicting those values. All right. I unfortunately can't show it. I apologize for that. So I'm going to come back and talk a little bit about the different evaluation metrics. So I talked about the grid search and how we would have different values of K, and we would try maybe multiple distance metrics. In this screenshot, it's showing just the Euclidean distance itself. And we have these different metrics that we try. So what I was showing before, a grid search with choice, is actually something where the data scientist chooses different values manually, and then we try it in, say, a loop. There also another way to do it is to randomly choose a value between so you would say between 1 and 10, randomly choose 5 K values to put into your model. So that way your input might not bias the results. And then there's a Bayesian method that actually takes what your accuracy looks like and actually tries to use that information from your model to then improve the choice of the next hyperparameter and the next hyperparameter after that. So in general, the choice is the most common way to do it. And it's also good if you're a data scientist who kind of knows what overfitting and underfitting look like. You can go in and do that. The Bayesian would probably be a better method in most cases, but it's more difficult to set up. So when you would take your model and output the metrics from our validation data set. So you would have a predicted value here and an actual value here. And then by actually comparing the ground truth that we know and our predicted value, we can calculate accuracy. We can look at false positives and true positives. So accuracy tells you basically the amount of or the proportion of the different rows or values that you tried to predict, how many of them you got right. So the number correct over all of the values in your data set. So the true positive and the true negative will sit up here. And then you actually take that error value and subtract it from 1 to get, say, a 0.91 would be you got 91% of your the rows that you tried to predict correct. There's also something called a false positive rate. You've probably heard of this. So before, one of the examples that people usually use are, as an example, are mammograms. That, in order to calculate that, you'll have your false positives will be in your numerator, And then you'll have your false positives and your true negatives down at the bottom. So basically, the values that end up that are actually negative, or in this case, it would be that a first substance abuse treatment that we were going in, and then it would take the false positive. So when it actually incorrectly predicted that it was a repeat treatment. So the incorrect positive or the false positive appear over basically anything that was actually negative in our data set. The true positive rate is a bit different. So a true positive would be when we correctly predicted something as positive, or in this case, having 2 or more treatments for substance abuse treatment. And then we put that over the actual positives in the data set. So the false negatives, so we incorrectly thought they were negative when they were actually positive, and those true positives. So a more intuitive way to think of it would be a false positive would be when a mammogram predicts a woman has breast cancer when she actually does not. A true positive would be when a mammogram correctly predicts a woman has breast cancer when she actually does have breast cancer. Are there any questions about this before I move on? So you've probably heard accuracy used most often in pretty much any exercise that you have done with looking at something is right or wrong in a group of things that you're predicting. However, accuracy isn't always the best way, and it's definitely not the only way to evaluate your different model performance or evaluate your models. There's a couple other ways to do this. The first one, we have already talked about it, the true positive, it would be the true positive rate. And that's called precision. So that actually has, it predicts, it has the true positive up at the top, and then it has everything that you predicted to be positive at the bottom. So even it would have the false positives and the true positives. So how many of the positive values did you actually get correct? So how many that you predicted as positive did you get were accurate? And recall is a bit different. You can kind of think of it as the opposite. So it has on the top the true positives, and then at the bottom it has those that were actually positive. So how many of those that were actually positive did we get correct? This one is how many that we predicted to be positive did we get correct? So that's going to be a bit different. And it's going to, so for instance, with breast cancer, we would want to outweigh recall versus precision, because say a woman goes in, she does have breast cancer, and it predicts that she does not have breast cancer. If a model is doing that a lot, that means it has low recall. So if something has low recall, and especially in healthcare, it's really not good, because if we miss something that's there, a cancer that is actually there, that can lead to a misdiagnosis that more often is going to lead to death. The precision is very important too, but it's not quite as life and death, because this would be if somebody would come in, or many people come in, they do not have breast cancer, and it actually predicts that they do. So the consequences of that are not good either, but it's that they will get a biopsy that will maybe come back negative, which has consequences, but it's less likely to make somebody die. So in general, especially in healthcare settings, we're going to weight recall as more important than the precision. So that would be the same in the case that we're looking at today. We really want to get those repeat admissions individuals right more often. So we're going to weight that recall score. And in general, they're the ones that are harder to predict. versus that precision. So now we can come back and kind of understand this. I'm going to go over the F-score in a second. So precision and recall. So and recall would be, in this case, for the 0. So in this case, it's not predicting these zeros well in general. So those that were a first admission to substance abuse treatment, you can see that over there. So more often, it's actually predicting those values or those people that were there for a first treatment as those that had 2 or more treatments in this case. So we can see that by the lower precision and recall values. So we're also seeing in general that the accuracy in this model is particularly low. So we're seeing that it's getting 68% right. When I rerun this model, we get it up to, after trying many different models, it goes up to 76% accuracy. So you can see as K increases here, the accuracy increases as well, but it's still particularly low. And this is partially because the data is really messy and K nearest neighbors doesn't handle noise very well. And in general, it's not generally the most effective model. So if I was able to actually show this today, you would see virtually the same accuracy values for the Manhattan distance as well. You would see very little difference between these accuracy numbers and Manhattan difference. And that seems to be pretty typical as well. All right, are there any questions about this? So you can think of precision and recall as a trade-off. When one goes up, the other one's going to go down. So you can weight recall or precision more. The way that you would say weight, recall, or precision differently would be to change your cutoff. So by default, a model outputs predicted values. So we'll say this one is 57% chance of being a 0, or predicting that it's a first treatment. We would then say we would predict that value or that person would be a 0. You can actually move and not have that cutoff be at 0.5. You could then move your cutoff for the 0s and the 1s for the classification of them. Say if anything that's above 0.6, that will predict it to be a 1, and anything below 0.6 will predict it to be a 0 when we're looking at that predicted probability. That will automatically change in the precision and recall, and you'll be able to weight one more than the other. So because it's a trade-off, we need to have a score that really weights both of them and looks at how it's performing for both. The F1 score does that. You can almost think of this as an average between the two. So we have our precision and our recall. So on the numerator, precision times recall goes in the numerator. Then you add the precision and recall in the denominator and you multiply it by 2. So that's basically a combined metric judging the model performance by both the precision and the recall. One thing that you want to keep in mind here is class imbalance. That's why accuracy isn't always the best metric to predict or evaluate a model. And this was in a job interview, a data science job interview that I was in. It was for an insurance company, and they were basically an insurance company for an insurance company. So for, say, State Farm, if they had a claim that was a really, really high dollar number, so much so that they would have trouble paying that financially, they basically hire their own insurance company for those high dollar value claims. So the ones that would really, like, the business would make a dent if they actually paid those off. It's called a reinsurance company. So I was interviewing for a reinsurance company, and of course, the things that they're trying to predict, those high value dollar claims, are very rare. They happen not very often at all. So say in 1 million different claims, there were 100 that were a high dollar value claims, or 1,000 even. Say you're getting 90 out of the 100 incorrect. That accuracy metric would actually still look good, because out of all of them, you're predicting, so say all the rest, those negative values, you're predicting them correct. So they are negative, but you're getting, say, the 90 out of the 100 like high value dollar claims correct. Well, that's actually going to look like a high accuracy, but in reality, those high value dollar claims are what you care about, and you're getting almost all of them wrong. So in order to weigh and make sure that class imbalance would be taken into account, the F1 score is best when you have highly imbalanced classes. So for your target, one of your target categories is much smaller than the other. So you would, in that case, completely ignore accuracy in that particular use case. And then you would rely only on the F score in that use case. And so that's when you would not want to use accuracy, and you might want to use something else for another use case. And then for something where you really had to get it right for healthcare, you might want to look more at recall than you would at accuracy. It depends on your business use case and that account. Are there any other questions about this before I move on?
Hey, Kelsey, I had a quick question.
Mm-hmm.
So for this particular problem, it's a binary classification, right?
Mm-hmm.
They either relapsed or they didn't.
Yes.
So when you're choosing your K, are you just picking two and then they're in one group or the other, or is there another way to look at this when you talk about classifying the result there and judging the accuracy?
So K basically is how your model's set up. So it's how it's making that prediction. So it's going to take your nearest neighbors and find that distance, make them majority vote, and then predict that as the class. But every classification model outputs a predicted probability. So some values it might be more confident in than others. So in a binary classification, you have to have a cut point. So where you predict it to be positive or negative. And that's going to change the accuracy of how well it does that by the different Ks that you choose. And actually, I think just showing the results here. So you can see that in this case, the different Ks are, the accuracy is improving as it goes up. There might be some cases where a smaller K is better, but that varies because that's like the hyperparameter that you set ahead of time. So that you actually have to choose ahead of time, and it affects the accuracy. It doesn't really affect how many classes you're predicting, which is, I think, what you're saying. So the way that you would take that predicted probability and pick a 0 or a 1, that would be based on your cut point. Does that answer your question? Not 100% sure I got that.
Yeah, no.
Okay.
Yeah, you got it.
Okay. All right. Are there any other questions? And then I can go over the confusion matrix. All right. So we've talked a lot about false positives and false negatives, and I'm going to take this and really kind of zoom in. So this is called a confusion matrix, and it's one of the better ways to explain something to stakeholders, because machine learning models generally are a black box. and it's hard for people to understand. They can this is a pretty intuitive way to explain or talk about the accuracy of your model. So you can think of these as two axes. So your true label, so what it actually is for your entire model when you're predicting, is located here. The predicted label is located here. So we, in this case, in this quadrant, we predicted that it was a first treatment, and it was actually a first treatment. In this quadrant, we predicted to be a second or two or more treatments or a repeat treatment, and it was actually a repeat treatment. So you want a darker color in these two, if at all humanly possible. And these quadrants are when we got it wrong. So in this case, we predicted the actual value was there were two or more treatments, but we predicted it to be a first treatment. We're not making this mistake very often. So when we do make a mistake, it's sitting here where it was actually a first treatment, but we predicted that there were two or more treatments. So you just saw that a little bit in the numbers on the recall, that's where we're messing that up. But instead of showing a recall or a precision number, this becomes a lot more intuitive to people. So where are you making your mistakes? And that's in this quadrant. And the darker these are, the better we know that our model is. And you have this gauge over here where like here, closer to 0.8 of these are correct. That 0.8 of the proportion of that are in this quadrant. So this is pretty intuitive to people to explain false positives, negatives, and when we're making the mistakes. So that is one way to show the accuracy of a machine learning model. I think I'm going to save this one for next time because ROC AUC curves are a bit difficult to understand in a lot of cases. So I'm going to come back to this in the next class. But are there any questions about the confusion matrix? I think we have 3 more minutes, and next time I promise my code will work and I will show you exactly what you need to know. But hopefully showing you this screenshot helped some. All right. Hopefully this was helpful for you guys. I will, in the next class, be going over the ROC curves, and then I will probably move on to something called ridge regression, lasso regression. And then I might get in to decision trees a little bit. I won't get over most of the decision trees. I'm going to cover the lasso regression, ridge regression, random forest, and gradient boosted trees earlier than the other models because that's usually how I do feature selection is with a combination of those 4 models. So after we cover, probably in the next 2 classes, we'll cover mostly lasso and ridge regression. In the next class, we'll probably cover a little bit of decision trees. Then in the next one after that, we'll finish up decision trees, talk about random forest and gradient boosted trees. You can get feature importance that comes out just naturally from those models. And then we'll talk, after we talk about all 4 of those, how I would go about in reality doing feature selection for our, so we could take those features that aren't important, throw them out, and then bring them in to improve our models. Definitely be there for the random forest and the gradient boosted trees models. Those are almost always the best models. If you try multiple ones, they tend to be the most accurate, I would say 9 times out of 10. Maybe except for like going towards the deep learning area. So if you're looking at the supervised machine learning before deep learning, they tend to be the best. So I will cover that, those things in the next 2 classes. Are there any questions before we finish up? All right. Thanks so much for attending. Really appreciate it. Hope it was helpful.